In this video, we're going to be talking about topic 10, which is exponential functions, talking about exponential growth and decay. Now, before we start looking at the problems here, I do want to confess to you that we did not really cover exponential growth and decay in class. It will be a topic on the end of your exam. However, the end of your exam is curved in order to allow for misunderstandings about this topic because we didn't get a chance to cover it. So if this is confusing to you or you don't feel like you had enough time to master this topic by the time you take the test this week, that is absolutely fine. The test will be curved so that you don't have to worry about it. There are a couple of topics coming up on the test that we did not have a chance to cover in class because we wanted to focus more on the content that you will need as you move forward in math rather than the content that you will be using a lot less frequently. So we're going to talk about exponential growth and decay. Now we have two formulas that will be given to you on the reference sheet at the end of your exam that have to do with exponential growth and decay. And this one is the one we'll see more often. So the problems in this review section have to do with this formula. Now what you'll notice is this formula looks kind of similar to a geometric sequence formula because it basically is a geometric sequence formula. A means the same thing as a sub 1. So if you remember, a geometric sequence formula starts with a sub n, which is a sub 1. And in the parentheses, we would end up with the rate, which in this case, we already talked about a rate in geometric sequences. It basically just takes 100% and adds the percent change. So 1 plus the rate. Our formula didn't take into account the 100% that we would need sometimes when talking about percentages. And then the exponent t is basically the same thing as our n minus 1 exponent. So these are very, very closely linked, which is why I'm hoping that if you're taking the initiative to watch these videos and try these problems using this formula, that it should come a little bit more naturally to you now that we've studied geometric sequences. So let's see about using this formula to solve some of these questions. We're going to begin with question 27, which I know is a challenging question. Again, the test is heavily curved, so please don't freak out about everything from topic 10. Okay, so it says that this expression represents the interest that a credit union pays on a savings account. So we have 1.021 to the t over 3 power. 1 is your 100% of your initial amount that you deposit, and the 0.021 talks about the change over time. That would be the rate, except that the exponent is written improperly. So we're looking for the yearly interest rate, which would be expressed by the number t, except that ours is not to the t power. Ours is to the t over 3 power, which means that we're going to have to fix the way that this is written before we can see what the actual rate is. So what we want to do is we want to take this 1.021 to the t over 3, and we want to rewrite it so that it's just something to the t power instead. And the way that we can do that is we can take this t over 3 exponent, t over 3, and we can rewrite it as something times t. So if I want to separate the t from the over 3 portion, I have to figure out what it's being multiplied by. So it has to be multiplied by something that puts a 3 in the denominator and doesn't change the numerator. So t is actually being multiplied by 1/3. So if t is being multiplied by 1/3, that means that I can separate the 1/3 from the t. The order that we do exponents doesn't matter. So what I'm going to do is I'm going to take the 1/3 and apply it first, and then leave the t on the outside. So I have this 1.021. It's being raised to the 1/3 power and the t power at the same time. So I'm just going to go ahead and apply the 1/3 power first. So I'm going to plug 1.021 to the 1/3 power in my calculator, and it tells me that it's I'm going to use a whole bunch of decimals here, 0.00695, there we go, 1.00695, that's 1.01 to the 1/3 power, and the t power can stay on the outside alone. Now that we've gotten the t power alone, it looks a lot more like the parentheses in the original formula, and I'm going to be able to figure out what my rate is. My rate is whatever's being added to the number 1. So that number 1 is here, and the number being added to it is 0.00695. So this is my actual rate. This is R. What it wants is for this to be given as a percent, rounded to the nearest thousandth. So in order to turn a decimal into a percent, all I have to do is move my decimal place 2 spaces forward. So this is going to be 0.695%, and it's rounded to the nearest thousandth. The thousandth means the third decimal place, so 695. There's my thousandth right there. So that would be my final answer. All I had to do was take the original percent given to me and simplify the exponent so that the t was by itself. All right, let's take a look at exponential growth versus exponential decay. These are very easy to tell the difference between. If my original amount, my original 100% gets larger, that means that my number inside my parentheses is bigger than 1, so 1 or more. That means that I am growing. That's growth, because I take the original amount and I'm adding a value to it every time. So I'm increasing the amount every time. That's considered gross. If it's less than 1, that means that every time I multiply by a number, I'm making my original number smaller by a certain amount. That's called decay or reduction. It's being made smaller. So all I have to know, in order to find growth is just that the number inside the parentheses has to be 1 or more. It has to be greater than 1. So A has a number in the parentheses greater than 1. It's 1.25. That's big. B has 0.93. That's smaller than 1, so that's not growth. C has 1.07. That's larger than 1. It's also going to be raised to the third power to make sure 1.07 to the third power is even larger than 1. The next one has 0.85. That is smaller than 1. But 1.05 is larger than 1. So all the ones with a value inside the parentheses larger than 1 are growing. So those all represent exponential growth. If there's a parentheses with anything smaller than 1, that means that we have decay happening instead, depreciation. So speaking of growth versus decay, or appreciation versus depreciation, let's go ahead and take a look at 29. We have a ball being dropped from a height of 20 meters onto pavement. On each bounce, the ball bounces to a height that is a percentage of the height of the previous bounce. So what's happening is we're dropping a ball, and the ball is bouncing. And every time the ball bounces, it's going to bounce at a certain percentage of where it was before. And you're used to seeing things bounce like this. Each bounce, it gets lower and lower and lower and lower. Eventually, it'll stop bouncing completely. So that's what's called depreciation or decay. So the ball bounces to a height that's a percentage of the height of the previous. The height of the ball is modeled by this guy right here. And you can see that inside the parentheses, we have 0.6. So it gets smaller every time it bounces. Now what we need to do is find the rate of depreciation. A rate means a percent, and we want to find at what percent it's getting smaller. So remember, the original formula we're going back to says that our new value is going to be the original value times 1 plus the rate to some exponent. So what we're looking for is this number, and we're going to turn it into a percent. So how much smaller than 1 are we going? If this is a positive, that means we're growing. If we're subtracting from 1, that means that we're getting smaller. So what I want to do is figure out, how did I get 0.6 out of the number 1? I did 1 minus something to get 0.6. How much smaller am I getting? So to get from 1 to 0.6, I must have subtracted 0.4. So that's how much smaller I'm getting. So this was my rate. All I have to do is turn that into a percent. So 0.4 is 40%. So with each bounce, I'm getting 40% lower than I was the bounce before. All right. Question 30. Write an exponential growth or decay function to model the situation. Again, these formulas will be given to you. The one that you will use most often is a of t is the original value a times 1 plus the rate to the t power. So let's take a look at what these mean. Again, a is just like a sub 1. It means the original value. R is the rate of change. We have to write it as a decimal in the problem, but it's probably going to be expressed with context as a percent. And then t just means time in years. So if I'm talking about my original volume, I'm talking about the original whatever. In this case, we're talking about cost, so that would be the original cost. So that means a sub t is going to start at 45,000. So that's $45,000. Then we have 1 plus the rate. So it's depreciating at a rate of 20%. Depreciation means it's getting smaller. So in my parentheses, I'm actually going to be subtracting 1 minus 20%. 20% can be written as 0.2 or 0.20. It's the same. So 1 minus 0.2, that means I'm getting smaller per year. And that just means that I'm doing the t power, and t is years. And that's it. That's my formula. If you wanted to simplify it, or if the multiple choice answer on the CFE is simplified, it would be 45,000 times 0.8 to the t power. And you can see that that subtraction makes the number inside my parentheses smaller than 1, which means that I'm getting smaller over time. All right, let's take a look at 31. We have Ariana investing $6,000 to get ready for college expenses. So investing means that her money is going to grow. So that's appreciation, that's exponential growth. Her bank is offering an annual rate of 5.8% per year, and she plans to do this for 4 years. So it's asking how much money she will have saved after 4 years. So what we're going to do, again, we're going to be using that formula. A sub t is the original value times 1 plus the rate to the t power. And we're going to fill in these values that we're figuring out here. So our initial amount is the amount she's investing. So 6,000. We're going to have to multiply that by 1 plus the rate. And remember, the rate's given to us as a percent, but we need to write it as a decimal. This is 5.8%. If I want to write 5.8% as a decimal, I have to move the decimal space 2 spaces to the left, which is going to move it over here. So I'm going to need this 0 as a placeholder. So 0.058, that's the number I'm adding there. And last but not least, I need the t value. The t value talks about the number of time in years, and it says in the problem she's doing this for 4 years. So we just use the number 4 as an exponent. So if I do this calculation, it'll tell me how much she'll have saved after 4 years. So all I have to do is plug that in the calculator. It says round to the nearest dollar. So I get 7,517.85. So I'm going to round that up to the nearest dollar, 18. So $7,518 that she'll have saved after 4 years. And that brings us to question 33. A population survey says that the population of a small beach community is 3,500 people. The population has been increasing, that's growth, at 17% per year, and the following equation can be used to model this growth. So you can see that the 17%, that's 0.17, they've done 1 plus that number to get the value inside the parentheses, so we can see this is growing, it's over 1. And the first question is asking us to interpret this a little bit. Where will this graph cross the y-axis? Now, if you remember, if we look at a graph, we cross the y-axis when x is 0, so when the input is 0. In this problem, the input is t, so when t is 0. So let's take a look at what happens when t is 0. So g of 0. We're going to have to do 3,500 times 1.17 to the 0 power. Now, anything to the 0 power equals 1. So this is just 3,500 times 1. So 3,500. That is our place where we cross the x-axis. So that's our y value right there. So this is also asking us, what does the y-intercept indicate in the context? So the y-intercept talks about where we touch the y-axis. It talks about our starting value, remember? So it says, a population survey says that we have 3,500 people. So this is talking about the starting population at the beginning of this survey. So this is the starting population. The y-intercept always tells you about the starting value of something. So if we're talking about population, then this is the starting population. All right, let's take a look at 33. Choose from the following options the functions that are equivalent to this guy if the time t is measured in years. So what this is asking us to do is something very similar to the first exponential growth and decay. It's asking us to simplify some exponents. So what we're going to do is we're going to make sure that our exponents have something to the t power, and that's it. So one number inside, the t power outside. The number inside should be 0.83, and they should equal exactly 0.83. If they don't, and t is by itself outside, and the number inside is not 0.83, then it's not equivalent. So I'm going to rewrite some of these so we can see what they're going to be equivalent to. If we start with option A, 5,000, same number up front, 0.72 to the negative t and to the t power. Now remember, I can combine those exponents. The order that we do to exponents doesn't matter, but if I combine those, I end up with negative t squared as an exponent, which is not anything like just having t. So that's not it. It's not A. Absolutely not. Too many t's happening. We only want one t. Now for option B, the number inside is not 0.83, but the t on the outside is not alone. So what I'm going to do is I'm going to kind of regroup this. I'm going to do the 12 as an exponent first, and then I'm going to leave the t on the outside. So 0.985 to the 12th power. If I plug that in the calculator, I get 0.83, which would leave the t as an exponent on the outside. So that's actually equivalent. It doesn't look like it at first, but it actually is. So the 0.985 to the 12th power equals the 0.83 that I'm looking for, and the t would end up alone on the outside. So B is actually true. Let's take a look at option C. If I do 0.947, again, it's to the 6th power and the t power, so I'm going to go ahead and group those together to see what happens there. So I'm going to group this guy with the 6 and do 0.947 to the power of 6, I get 0.72, not 0.83. So it doesn't work every time. That one is also not a solution. For part D, t is already by itself as an exponent, and the number inside is 8.64. That is not 0.83, so that is obviously not a solution. And for part E, let's go ahead and take a look at what happens when I group those guys together. 0.83 to the 1/6 and to the 6th power. So that's 0.83 to the 1/6 times 6, and then to the t power on the outside. So 1/6 times 6 is just 6 over 6, which is 1. And 0.83 to the first power is just 0.83. So if I simplify those exponents, that actually does equal 0.83 to the t power. So E is also a correct answer here. All right, we have one more question about growth and decay. Let's take a look here. Choose from, two more questions. Just kidding. Oh no, I copied that one in twice. Haha, we already did that one. JK. Okay, let's take a look at question 34. Y equals 30 to the 1.2t. Now, the first question is this growth or decay? And we have now learned that growth means the number inside the parentheses is bigger than 1. So this is growth. What is the percent rate of change of y with respect to t? So that's just asking for what the rate of change is as a percent. Remember, in the equation, it's going to be a decimal, but when we talk about the rate, we're going to write it as a percent. So what happened inside my parentheses? I had 1 plus my r, and in this case, I have the number 1.2. So what did I add? 1 plus some number is 1.2. This number tells me my rate, and I must have added 0.2. So 0.2 is my rate. All I have to do is write that as a percent. So I move the decimal place 2 places over, and I see that I get 20%. So that's my rate of change here. So 20% per time unit. And that's it. So that's your mini lesson on exponential growth and decay. Remember, if these didn't make a lot of sense to you, it is okay. The test is heavily curved, and if you don't have the opportunity to answer these questions correctly, that is fine. It won't really count against you in the long term as long as you understand everything we did learn together decently well. So make sure you keep up with your review, okay?